I know that y'all are all excited about doing your group analysis and playing with feedback and multiple and correction for multiple comparisons, but we do have to move on. So for this talk, we'll change gears a little bit, and still we're talking about testing inferences across groups of subjects, but we're going to talk about doing it inside of regions of interest. And so FreeSurfer has a very rich set of results that are related to region of interest analysis. And so what this talk does is introduces you to what those different data outputs are and how they are generated, and how you go about exploiting them. In addition to having a very rich set of data outputs, there's a lot of terminology that goes along with the regions of interest that's not entirely obvious if you just start looking at it. So we'll talk about segmentations and labels and parcellations and annotations. And all of those kind of mean very similar things, but it's helpful to get the nomenclature right because there are some subtle differences between them. So the first thing that I'll do is talk about some ROI studies just to make sure that we're on the same page about the kind of thing that you want to do with ROIs. And then I'll teach you how to export the ROIs into a table that you could then import into Excel or SPSS or something like that. And then I'll go through the nuances of FreeSurfer terminology in terms of ROIs, and then talk finally about statistics files. So this is a slide that Bruce presented way back yesterday morning, which must seem like an infinity time ago to you, but that certainly does me. And this slide has 4 bars on it, and each one of those bars represents a different group, and the amplitude, the height of the bar is the left lateral ventricle, the volume of the left lateral ventricle as a percentage of intracranial volume. And so even though there are 4 bars there, at the time that these subjects were scanned, there were only actually 3 groups. There was a group on the left, the blue group, which is the healthy group, the group on the right, which was the group that probably had AD, and this group in the middle that it was unclear as to whether they had AD or whether they were healthy or not. And so 3 years after the scan, they continued to follow these subjects, and some of them converted into Alzheimer's disease, and some of them did not. And so if you go back 3 years from that conversion time and look at the volume of the lateral ventricle, what you see is the light blue bar is much closer to the healthy subjects, and the yellow bar is close to those who had AD. So even 3 years before diagnosis, it was possible to distinguish the subjects who were not going to convert in 3 years from those subjects that would convert in 3 years. So this is just an example of a region of interest study where you're not looking at a FOXA-wise difference across the cortical surface or across the hippocampus or across the ventricles. What you're doing is you're just collecting one number for the entire region of interest. In this case, that number is the volume. And you're comparing that one number between these different groups. So this is our subcortical segmentation, which you've already seen a couple of times already. This is called the ASEG, which stands for automatic segmentation. And so the paper that documents this is down below. It's from Bruce from 2002. And this just shows the different regions that we segment. And so it's hippocampus, pallidum, caudate, white matter, thalamus, putamen, amygdala, nucleus accumbens, cerebellum, brainstem are all there. And so this is a volume, and every voxel gets a value, and that value indicates what cortical brain structure happens to be in. See up here at the top where it says cortex and it says it's not used, and a lot of people look at that and say, well, if it's not used, then what are you doing? The reason why it's not used is that we have a whole surface-based cortical segmentation routine that we go through in order to really finely and accurately and in a sub-voxel way estimate exactly where cortex is. So the reason why it has to be on here is that you have to label every voxel, or you can't label any voxel. So we have to label cortex, and that's why cortex shows up in our volume-based label, but we don't end up using it because we have something more accurate later on. So this atlas, so we have an atlas that has all of these labels in them. And so the atlas is probabilistic, that is, it was generated from 39 subjects. So for every point in the brain, we have a probability that that point in the brain is, say, hippocampus, or that that point in the brain is ventricle, or that that point in the brain is white matter, or that point in the brain is cortex. So we have a probability based upon these 39 subjects. So based upon that probability and some other things, including the actual intensity of your individual subject at that particular voxel, and and whether, like, you know that hippocampus and amygdala are, that hippocampus is always posterior to amygdala, for example. So we take all of that information together along with information from the subject scan, and we apply that, and then for each individual, then we can create one of these customized maps of subcortical structures or all of the entire brain. But primarily we use the ASIC for extracting out information of subcortical structures. So so this is a labeling individualized to each subject as to what each individual voxel is. And so that's what so once we have that, then we can extract out volume, say, of hippocampus, volume of ventricle, volume of amygdala, for example. In addition to having the volumetric labeling, of course, we also have the cortical labeling. And this one is the APARC. This is the Desikan-Kiliani atlas. And so this is an example of an ROI study that you might do with a cortical label as opposed to a subcortical label. So here I have this arrow pointing to ventral cortex, which is this red area. And for these same four groups, I have these error bars indicate the average thickness for each one of the groups. So this is, the first group is about 3.4 millimeters thick on average in entorhinal cortex. And as you can see, the two healthy groups have a larger or thicker entorhinal cortex, and then the unhealthy AD groups have a much thinner one. So this is known that an entorhinal cortex becomes devastated in AD. Additionally, we could look at a different ROI, and we could look at a different metric. So we have three metrics for every ROI. We have average cortical thickness, and so that's an average over the entire region. And we have the total area for the ROI. So if you remember, our surface model is a mesh model that has a whole bunch of triangles. And so when we do this labeling, we're simply assigning each triangle to be in superior temporal gyrus, entorhinal cortex, precentral sulcus, whatever. And so all we have to do is go and count up the area of all the different triangles, and we get the area for the region of interest. And so that's one number for the entire region of interest. And it's shown here if you wanted to do a study of that. You can see that the area for middle temporal gyrus in this case is something like 2,700 square millimeters, and that there are differences across these groups. In addition, it's possible to do total volume. So if you take thickness and you multiply it by area, you get the volume for the region of interest. So as I mentioned before, this is the Desikan-Kiliani atlas. And so this was done, what year was this? A number of years ago. And so this has, I think, I can't remember the exact number of regions. I think it's something like 20 regions per hemisphere, 35 regions per hemisphere. And these are gyral parcellations, that is, they go from the fundus, the valley of one sulcus, all over the gyrus to the valley of another sulcus. So this is a gyral parcellation. It was done by Rahul Desikan because he's mainly interested in looking at changes with Alzheimer's disease. And so you have 35 of these per hemisphere. And so the way that this works, as I described yesterday, is that when you're running recon all will register your individual subject's hemisphere to FS average. And so we have one of these maps on FS average, and so we map that back into the individual subject space, and then the boundaries of it get adjusted. So after that, that's the labeling process for the surface-based methodology. The Desikan-Kiliani Atlas is 40 subjects, 14 male, 26 females, ages 18 to almost 90, 30 non-demented, 10 demented, done on Siemens 1.5T. Mostly we find that these things don't vary a lot. The accuracy is pretty robust with these surface-based measures because it's measuring from fundus to fundus. So as long as your surfaces are accurate, then in general these mappings are pretty good, regardless of the fact that the atlas subjects, the subject used to generate the atlas, might not match your individual study all that well. There is another atlas. So we have all kinds of ROIs. As I mentioned before, we have all kinds of data. It's a very rich data set that FreeSurfer generates to characterize your subjects on an ROI basis. So you've seen the ASEG, which is the volume segmentation. You've now seen the Desikan Atlas, which is 35 cortical regions per hemisphere. This is the Destrio Atlas, named after Christophe Destrio, which has 58 ROIs per hemisphere. This is only generated from 12 subjects. And so a lot of people will come and say, okay, which one of these atlases should I use? And the answer is always, it depends on what it is that you're trying to do. So my preference is to use, because you have 58 units in the Destrio atlas, each unit is going to be much smaller. So if you just look back and forth between these two, you can see that Christophe's parcellation has much smaller units than Desikan was. So that's good because it gives you more detail, but it's also bad because because the units are smaller, they might not be as accurate. So you have to keep that in mind. On the other hand, it might be that you're really interested in something that the Desikan Atlas, combines 3 of the Destrio Atlas labels into one big one. And really what you're interested in is something that's smaller. And so in that case, you might have to go with the Destrio Atlas. There are also ways to take these ROIs and divide them up into halves or thirds or quarters or fifths or whatever you want to do. So it's possible to slice and dice these things to try to customize it to something that you're interested in. So, but you should keep in mind that it's just geometric division. So the Desikan and Destrio atlases are driven by cortical alignment to a probabilistic atlas. So it's trying as best as it can to get the anatomy lined up properly and have these ROIs defined anatomically. I think I added this. Oh no, this is what you have. So it's possible also to label white matter. So if you look in here in the APARC plus ASEG, you see this big white structure, which is the left hemisphere white matter. You see this big green structure, which is the right hemisphere white matter. And it's all one label. And so because white matter may be not as interesting as gray matter to some people, still an interesting tissue to study. And so, but white matter on an MRI, on a T1 weighted MRI scanner looks pretty much white. There's not a whole lot of anatomical boundaries, even though there are a lot of tracks and stuff like that going through there. So in order to do an anatomically based segmentation of white matter, the way that we did this was to label each point of white matter based upon its proximity to a cortical gray matter structure. So that's what you see over here on the right side. So, so where this red plus mark is, you have this, this blue gyrus around there, which corresponds to this blue gyrus, which is precentral gyrus. And so you can still see over on the right side this blue gyrus as well. But now the white matter associated with it is this yellowish color. And so all of that is white matter that's within, I think, 5 or 7 millimeters of cortex. And that white matter just happens to be closest to the precentral gyrus of all the other cortical structures that it could be close to. It's closest to the precentral gyrus. And so all of these colors that you see inside here are labels of white matter based upon the distance to the closest cortical label. So it's kind of creating more information, but maybe not really. So it's not parcellating the anatomy of white matter based upon tracks or anything like that. It's just proximity to the cortical gray matter. And so this has actually been used by David Slott to look at the changes in these volumes associated with age. So if you remember your FreeSurfer output, here's your subject stir, which is your environment variable, where FreeSurfer is going to put all of these different subjects. In subject 2, you have an MRI directory where you're going to have the automatic segmentation. You'll have the white matter parcellation as well. And these are all volumes because they're under the MRI. In label, you have the APARC, which is the Desikan Kiliani Atlas. And you have the APARC and A2009S, which is the Destrio Atlas. You know, this is what I mean, that you have all these different names for different things, and they all kind of are similar, but you have to know what each one of these names means. And then finally, you have stats files underneath there, where you have aseg.stats, and these are simply text files that have tables of data in them. So the aseg.stats has a text file that has the volume of hippocampus, the left hippocampus volume, right hippocampus volume, left amygdala volume, right amygdala. It has all of those structures and the volume for all of those structures that are in there. And as does the wmparc.stats. And then all of these stats files are just simple text files that have tables.
Do you have a parcellation of white matter based on at the lobular level?
Do we have a parcellation of white matter based upon the lobular level? We do not, but it would be something relatively easy to generate. So for every subject, you have these stats files. And so if you have 50 subjects, you'll have 50 sets of these stats files. And of course, you'll want to take them and combine them together so that you can go off and do your own cool region of interest study. And so the way that you do that is with this program called aseg stats to table. And so you give it a dash subjects, and then you list all of the subjects that you want. And you say that you want to extract out the volume. And you say that the stats file is aseg.stats, and then you give it an output table file here, and you say aseg.table.txt. And so this is going to be a big table, and every row is going to be a subject, and every column is going to be a region of interest, and the value at any row column is the volume of that region for that particular subject. And I'll show you later that you can, yeah.
And the subjects line here, would that be like the name of the recon directory for each subject, or just the subject name itself, and it knows to look for recon attached to it?
It would be the name that you pass when you run recon all. So in this case, you would say recon all dash subject 001, and then dash all. So then it looks for 001. So there has to be a folder there called 001. So with the ASEC, the main thing that you're going to be interested in is the volume of the structure. Maybe it's possible to look at, say, the mean T1 intensity. I'm not sure that would be very informative. But mainly for the ASIC, you're only looking at volume. But for the cortical structures, there are, remember, 3 things that you can look at. You can look at the average thickness over the cortical structure. You can look at the total surface area of the structure, or you can look at the total gray matter volume of the structure. And so to do this, we have a different program called APARC-stats to table. So here's where it starts to get a little bit confusing, because we have, if things were done in a volume setting, so we have labels of, in the volume of the brain, like subcortical structures, then that's called an ASEG. If it's done, or segmentation, and if it's done on the surface, that's called a parcellation or an annotation. And so we have an ASEG stats to table, and now we have an APARC stats to table. An APARC stats to table does basically the same thing, where you give it a list of subjects. In this case, you have to tell it which hemisphere you want, because surface-based analysis is done in left hemisphere and right hemisphere separately. In this case, I give it the measure of thickness, and I tell it to use the parc equals APARC. So this is the desiccant atlas. If I wanted to use the destrio atlas, I would have used parc equal APARC.A2009. Sorry, I know it's really tedious listening to me like spill out abbreviations. So anyway, but the main thing here is that you give it a list of subjects, give it the hemisphere, and you say that you want to look at thickness, and then you have a table file, and it's going to spit this out, and every row is going to have a subject, and every column is going to be a different cortical region of interest, and the value at a given point is going to be the mean thickness for that subject at that ROI. So the other things that you can have are area, and the only thing that you do is to simply change measure here from thickness to area, and you get a new table out. And then you can also say volume as well. You just change measure from volume, from thickness or area to volume, and you get another table.
For the thickness measure, is that the blurred thickness measure, or before?
What do you mean by the blurred thickness measure?
If you do a full width of half maximum of 10 millimeters, is that
So in this case, you would not be smoothing the data. This just looks at the raw data, because you don't need to smooth, because you're averaging it over the region of interest.
Yeah.
So once you have these table files, then you can export them or import them, depending on how you want to think about it, into other programs such as SPSS or MATLAB or Excel or OOCalc, which is the Linux version of Excel. And so in your tutorial, you'll be working with OOCalc and just load this thing up into that so that you can be able to work with this. This makes things very, very simple to work with. You can just export it out of FreeSurfer, and then FreeSurfer is out of your hair for a little while you're doing your ROI analysis. If you like having FreeSurfer in your hair, then you can do the GLM analysis inside of FreeSurfer itself using MRI GLM fit. So you're already familiar with MRI GLM fit from Eugenia's talk and the tutorials that you went over. And in this case, instead of giving it a --y to indicate that you have image-based data, use --table and you pass it that table. And so remember that table has a list of, it is a number of subjects by number of ROIs. And it basically just treats every ROI as if it were a different voxel or a different vertex. And so it just goes off and performs your statistics on those ROIs. And so this can be handy because then you just have one statistics program, which is GLMFET, and you can apply that one program to your pixel data, and you can apply it to your ROI data. And so then everything else is basically the same after that. So we have this APARC plus ASEG, which I've mentioned a couple of times before. And so that starts from the ASEG that just has one label for cortex. And it just goes and inserts the actual cortical label in there. So it replaces this one big red region of interest with all the regions of interest from the APARC. So there's not actually any new information that's being created there. It's just a better way to visualize your data if you happen to be looking at, say, your fMRI data and you want to visualize it on volume. For an individual subject, it's much nicer to visualize it on this volume because then you have access to all of the regions of interest.
Is it correct that the A park does not have to fill in every voxel?
Is it correct that
So-
the A part does not have to
Just
fill?
meaning that ASEG has to label every voxel, but the A park will
Oh,
have...
the A part has to label every single vertex in cortex. So it's only working on cortical structures.
So
But
it
it has,
maps back into this voxel space.
right, it
Would
maps
that be-
back into the voxel space. So now we've gone over ASEG, which is the volume-based segmentation, the Desiccant atlas, the Destrio atlas. And so now we're coming to the, we have several different other regions of interest that can be generated. And this is just one of them based upon ex vivo data. So these are Brodmann areas that were labeled cytoarchitectonically. So on ex vivo, so people had died and they scanned their brains and then they sliced the brains and then stained them and figured out which areas were EA1 and 2 and 3A and B and 4A and 4P and 6 and 44 and 45 and MT and E1 and rhinal and E2. And those were based upon the ex vivo data were mapped onto the surface and we created a probabilistic atlas for all of these different areas. So those exist as well, so you can do the same kind of thing, extracting out, being thickness or total surface area or total volume for these things as well. And I'm really just scratching the surface. I can think of at least 2 more ROI atlases that we have, one based upon functional connectivity. So I'll change gears here slightly and start talking about these ROIs more specifically in terms of FreeSurfer and how do you actually navigate through FreeSurfer to understand these ROIs. So when I say ROI, it can mean segmentation, it can mean a parcellation or an annotation, or a cluster or a mask, or a label that you draw by yourself. So the segmentation is, it's usually a volume. It's in a volume style format like an MGZ or an NIFTY or something like that, most likely an MGZ format. And each voxel or vertex gets a single value, and that value is an index. And that's an index into a lookup table. So it's just an integer number, 1, 2, 3, 4, 100, 200, whatever. And so we have several different lookup tables. And the most prominent one is this one called FreeSurfer color LUT.txt. And if you look at this, it's going to be a table. And every table and every line is going to be a different region of interest. And so the first line, the first item in the line is a number, and that's the index. So in this case, 17 is left hippocampus. And if you looked inside the ASEG, you see this yellowish kind of blob there. And so every value inside of that yellow blob is number 17. So in FreeSurfer, when FreeView loads this up, it says, oh, that's number 17. I'm going to go into this lookup table and find number 17, and it's going to see, okay, that's left hippocampus. So I'm going to print left hippocampus down at the bottom left. And the color that I'm going to give it is going to be this RGB. So red, 220 out of 205, so lots of red. 216 for green, which is a lot, and a little bit for blue. So mostly this is going to be red and green, which makes yellow, which gives you this little yellow blob there. So again, this is what we call a segmentation, and it refers to volume-based labeling, where you're assigning a value to each voxel, and that voxel is an index into a lookup table. Next, we have something called a parcellation, also known as an annotation. And these apply only to surface-based labels. So the annotations are something .anot, such as lh.apart.anot or lh.apart.a2009.anot. And each vertex, again, has only one label or index. And but the actual indices and names are actually stored inside the annotation, although you can also find them in this FreeSurfer color lookup table. So the third format is a label file. And so this is something that you can create yourself. So when Rahul Desikan created the Desikan-Kiliani Atlas, what he did was he took his 39 subjects and created labels by drawing them by hand on each brain. So he did that 39 times by 35 per hemisphere by 2 hemispheres. And so what that means is to go in, I think maybe you've already drawn a few ROIs already, and to manually go in and pick out points and set up points like this, and then it'll connect all of the points and close that loop. And that's how you would create a label. So and then it's stored as a simple text file that just has a list of vertices and their X, Y, Z coordinates. So in a way, this is the simplest type of file. They're relatively easy to draw, and you can do so in Freeview and TKNet, FreeSurfer, and QDEC, I think. So, and you can find examples in the label directory. So we actually create several labels automatically as part of FreeSurfer, including these Broadman area labels. So if you want, you can just look at one of those in the text editor. So the statistical outputs again are these stat files. So there's the ASEG and WMPark.stats, and those are volume-based. And then anything with an LH or an RH in front of it is going to be surface-based. So the statistics files, and again, I apologize, this is rather boring, but if you're going to be asked in the next tutorial to open up these statistics files and just take a look at them to see what's inside. And so in this case, the first column is just the row number, and the second column is the segmentation ID. So here we have number 17, which is left hippocampus, and then you have the volume, and then you have mean intensity, which is the mean T1 intensity, and then you have some statistics on the intensity values, which are probably not very interesting. This particular file has some header structure with it that includes total cortical volume for the left hemisphere, total gray matter volume for the right hemisphere cortex, total volume of left and right together, total white matter volume, total left hemisphere, total white matter volume for the right hemisphere, total subcortical gray matter volume. So all of these kind of global measures are stuck in this table as well. And probably the one that you're most interested in is going to be the intracranial volume, because that is an estimate of the total intracranial volume. And I think I have another slide on that later on. Actually, I'll just go ahead and explain it right now, because this generates nothing but confusion in terms of how this number is generated. So there's a number that'll come out that will say intracranial volume or estimated intracranial volume. And so where does that number come from? So as I mentioned earlier, which you might not remember, you cannot see the skull on MRI, on typical MRI. So you'd have to use like a CT scan, and then you could find out where the skull is. And if you had a CT scan, then you could go and count the number of voxels inside of the skull, and that would be your intracranial volume. So we cannot do that in MRI. So we have to resort to inferior methods. And so the inferior method that we use is to register the subject with its skull, with the whole skull that you can't see, but the tissue on the outside of the skull, to a Talarex space. And based upon that registration, we create an estimated intracranial volume. And that is what shows up in this table. So it's not the real intracranial volume you would get from a CT scan. This is an estimate. And so one of the things that means is that if you were to scan the same subject twice, you would get a little bit different of an estimate from one scan to the other. So just want to be clear on that because it just generates all kinds of confusions. So Randy Buckner was the one who developed this technique, and he has a paper which you can get off of our wiki. So that was this, okay.
It's about the estimate to measure cranial volume. Does it get affected if we had bad skull stripping?
Does the estimate of intracranial volume get affected if you have bad skull stripping? It does not, because it's only generated based upon this registration and the registration is done before skull stripping. Okay, so that was the ASEG file, and if you look in the ASEG file, you can't see it here, but you can see that there are all these left lateralized structures, but the right ones are also in there as well. So this is the volume of left hippocampus and the volume of right hippocampus will both be inside of these ASEG files. So the parcellation stat files are for the surface structures, and they have a different structure to them. So the first column is the name, the cortical parcellation. Then you have the number of vertices, which is actually not very interesting. Then you have the surface area, which is interesting. You have the gray matter volume, and then the average thickness, and then some other stats that are really not all that interesting. There's more information on the global stats in this morphometry stats page. So to summarize here, you have lots and lots of regions of interest that are customized to your individual subject inside of FreeSurfer. So you have subcortical and white matter regions of interest, which are mainly just a volume, so volume of hippocampus, volume of some white matter structure, volume of brainstem. And you have surface regions of interest that have three numbers associated with them: the total volume, the total surface area, and the mean thickness inside of them. You can take these and extract them out to tables, which you could import into SPSS or MATLAB or whatever, or run using MRI-geolimfit. And the nomenclature is